we're going to be talking about OpenTSDB and also time series schemas of some other databases, MySQL or SQL-ish schemas, all that kind of stuff. So I want to talk about who I am. I'm an engineer at Yahoo. Joined there about 2 years ago. I'm also the lead maintainer for OpenTSDB, open source, and also in-house at Yahoo. And about who I'm not a marketer. I'm not a salesperson because we don't have a business set up around OpenTSDB. So I'm not going to try to sugarcoat all the things that OpenTSDB does wrong or has problems with. And I'm not going to be saying, oh, it's the greatest thing, sliced bread. But I'll try to be as truthful about what it's good for, what it's not good for, what's coming up in the future, all that fun stuff. So, of course, if you've been here before or been listening through the conference at all, we've been talking about time series, and you should know what a time series is. It's simply defined as a discrete set of values ordered and indexed by time, right? And those values can be all kinds of things. So, and they're always associated with an identity of some kind. So you can do lots of fun stuff with your time series. You can graph it, get eyes on glass, look at things, see if there are problems, jumping out, look for patterns. Almost nothing recognizes the patterns as good as our wetware, right? Although machine learning is getting better and better, I guess. And you can also run analytics on the raw data, all that fun stuff. The discrete values are always data points. So a single data point is going to have your identifier. It may have dimensions that add to that identifier in newer systems, and it's going to have a value. And that payload, in general for time series, people think of it as only numeric data, but it can also be other kinds of data like event data, strings, Git commits are a form of time series, right? And then you can also store other things like raw binary blobs, and then in the monitoring world, histograms, things like that, digests, sketches, those kind of things are super important to be able to store, and they're not specifically numeric, they're combinations of data that have to be aggregated in a certain way, and I'll talk about that maybe at some point. So for today's talk, because it's not HBase Con, it's not time series con, I kind of wanted to try to bridge the gap between the RDBMS world and time series NoSQL land. So I wanted to say, here's some scenarios you could pick through for yourselves, and maybe you've been through some of them in the past whenever you've encountered time series data. So maybe you're a dev and you want to instrument your code, or maybe you're a scientist and you want to run experiments and track results over time. And so whichever scenario you want to pick, the first place a lot of developers start is to write time series into flat files. So the benefit of that is that it's super easy to write some code and say append to this file, and then, or open, append, close, etc. And then you can take that file, you can compress it, share it, back it up, distribute it, email it to people and say, hey, look at my cool results. Go do something with them because I don't have a GUI or anything. So that's one benefit to it. And once you have some of this data lying around, you might show your numbers to your coworkers and they'll say, oh, that's cool. Can I use what you did? I want to reuse it in my project or something. And so you say, okay, yeah, hey, that's cool. But then once you start playing with that some more and you say, oh, well, having lots of these little files around, it's going to be a pain to manage. It's not easy. You have, if you grow and write more and more data, you're going to start thrashing your disks, your I/O, regardless of if it's SSDs or spinning disks, or even if it's memory, you're going to be writing and rewriting and all that fun stuff. Plus, if you want to do anything useful like graph that data, besides importing it to Excel and graphing it, if you want to start merging these data sets, you have to write some code and do it yourself. So one of the natural places to turn to, being a MySQL kind of convention, is to look at the RDBMS, right? So back in the 70s, we started seeing these popping up. They have the benefit of that you can write to them from lots of locations. Has a great built-in query language that you can do all kinds of cool mathematical operations on the data. You can group it, sum it, all that fun stuff. Yeah, there's replication, well-known tools. You can back it up. And then you have tons of vendors to choose from, too. So maybe you've seen schemas like this, super simple. You have a timestamp, you have some kind of identifier, a metric name, and then you have your value. And bam, you've got a time series database, right, in SQL. So that's awesome. But now your coworker is going to look at that and say, hey, this has been fun. I love being able to write to SQL, use my tools. Now I'm going to start giving you more data. And all of a sudden, your SQL database is going to start bogging down. Your writes are going to get slower and all that because you're going to have bigger and bigger indices in the single table. And it's just going to take a lot longer to query that data. It's going to take longer to delete it if you want to get rid of the old stuff. So the next logical step a lot of people take is say, well, heck, I'll just shard my tables and I'll split it up by day or hour or something like that. Problem solved, yay, right? Well, not always. I mean, you can query this data, you can join on it in app or in SQL. You can write stored procedures, do all that fun stuff. And your coworkers are going to be happy with you for a bit, and then they're going to say, oh, somebody in the mail group or Flickr or Tumblr, hey, they're starting to send a whole bunch more data, and they brought down the database for everybody now because they're sending so much stuff to us. So this helped a little bit, but then it doesn't get you very far when you start pushing more data. You have the same problem still. So another step might be, okay, I want to save space. So I'm going to convert all those strings into UIDs, so I only store the string once, which is really useful if somebody tries to print out the DOM of a website or a web page, and it's, 25 megs in length or something, and they want to use that as their identifier, which has happened on accident, usually. Or if they have giant unique strings, so hey, I'll convert it into IDs that I can then join on in my RDBMS. I'll split my tables up by groups, and then I can either offload those shards to different MySQL servers, or I can just maintain the tables, and I'll do all that fun balancing, and hopefully it won't bring it down. Now, of course, your query is getting a lot more complex. You're joining and having all that kind of fun to deal with. And your coworkers are like, great, oh, I love this UUID system. I can add tags, and now I can search for things and do things like show the network traffic for my data center in Phoenix versus New York versus Amsterdam, etc. Can I also start storing some strings in there and all of that? And then it turns out that this kind of extension still is going to be a pain in the neck because it doesn't support other types than numeric data unless you extend the schema. It's still going to require all of your complex routing code and sharding and all of that fun stuff. So at this point you might say, well, let's look and see what other solutions are out there. It sounds like time series are kind of taken off. So some of the problems that are common to all of time series data sets that all of the solutions that are out there are going to try to help you with. One of the important ones is being able to handle unbounded metrics and dimensions. And by dimensions, I mean things like you have a tag name that says host, and then you have tag values that might be the unique hosts in your data center and all that kind of stuff. So when people get into this kind of measuring system, they're going to tag their data because they want to slice it up on different aggregates. Like maybe I want to look at traffic by colo, or show me the top offending hosts, or show me these applications that are running on these types of Docker images and virtual machines and that kind of stuff. Another important problem with that is cardinality. Every database engineer should be familiar with cardinality. Same thing in time series, where you might have a single tag and you might have millions and millions of possible unique values for that data. Doesn't necessarily mean all million data values are being written at the same time. It may be sparse data, or it may be consistent data that's coming in, but you have to be able to deal with that. Another thing is to deal with wide-ranging queries. So if you're in the monitoring sphere, you're looking at the last hour of data, last 6 hours of data. But then if you want to do capacity reporting or something, you're going to look at information in your system over a year or months or days. And when you ask for that data, if you try to pick out raw values at every second and try to graph that, first your graph library, if it makes it that far, is going to yell at you and say, why are you giving me so many data points to plot in a little 200-pixel graph? That's just stupid. Or your database is going to say, hey, this is too much data to ship over the wire. So you have to watch out for that. And some systems will provide for rolling up data to a lower fidelity that you can then plot for wider time ranges. Another thing that's important, again, is to aggregate data by different tags. So doing that analysis by colo in this case. Also being able to perform actual useful analytics on top of that data, like calculating percentiles, moving averages, all that fun stuff. And then, of course, because you're going to be serving somebody, you want high availability, you want replication, high uptime, all that fun stuff. And then be able to push a lot of data through. So how many people are familiar with RRDTool, Mrtg? Really? Not too many people? So back in the 90s or so, this was one of the first, earliest implementations of a time series specific data store. And it works. It created these neat graphs that you could, PNGs that you could share around. And, you know, if you ever bought colo facilities or data center traffic, you'd see these Mrtg graphs, and they'd say, all right, that's why we're billing you $1 million this month, because you spiked up here. You know. And the way these worked is that it used a simple circular buffer on disk, in that you'd say, okay, I want to store 100 data points, 1 data point every minute, and then as you write the data, it fits it in a slot, and once you reach the end of the buffer, it just circles around and overrides the old data. So the benefit of this is that you have a very fixed file size for a particular time series. You're never going to worry about filling up your disk space if you're only writing to this one metric. And also the RRDTool library had some neat graphing functions built in, had some rudimentary analysis that you could do to calculate some synthetic values on top of that, and then it also was able to downsample or give you the lower resolution data in the same object. Problems with that is that if you wanted to write a lot of time series, you had to every time open this file, modify it, and close it, and that leads to a lot of I/O disk thrashing. It also lost some precision. I didn't mention that up here, but it creates those buckets, and then if you write a timestamp anywhere within that bucket, it's going to align that timestamp and do some interpolation. So that's one problem. Then another is that you don't have any replication, high availability. You could put it on an NFS share or something like that. That could help a little bit, but there wasn't much in the way of management or all that fun stuff. And then aggregating across these different RRD files, you had to do yourself somehow. And I think the library allows for some of that. Then there were a couple of time series databases proprietary. I don't know too much about these guys. I don't know exactly how they store them, but one of the big ones was KDB, and this was used in the financial industry, still is, for stock analysis in the background. Then IBM had Informix, and they added a time series specific implementation for that. And so it's great in that now you had commercial companies that you could go and throttle their necks and say, hey, why isn't this working? But then you had to pay fees associated with that, of course, right? And there's also very little integration with open source projects for these guys. Later on, we got Graphite out of Orbitz, which was pretty much just a fancy wrapper around RRDTool, which gave you a nice UI that you could load up in your browser. You could start saving dashboards based on this information. You could drill down based on how you put dots in the name of your RRD files into a hierarchy and explore your data. And this has kind of been the industry standard for a long time for small-scale startups, people wanting to monitor some of their systems. You just spin up a Graphite server somewhere and you start pushing data into it. And it works really good. It's pretty nice, except that you face the same kind of problems with RRDTool. Even though they've moved to a different backend called Carbon, it's still RRD based, same kind of file format and all that, so you're still thrashing your disks. And I know of a lot of companies who have had Graphite, they move on to SSD and they get some relief, but then eventually, even after that, they are still overloading their SSDs, and they try sharding to different instances, different servers, and it's just a pain in the neck. So one good thing about Graphite is that they are working on plugins that will allow you to work with different time series data stores and still use their really nice GUI. And then in 2010, OpenTSDB came along. So OpenTSDB is kind of based, it was started by an engineer from Google. It was based kind of on their internal system that they had for measuring some time series data. It's capable of storing millions of data points per second, and it's not nifty-boast. This is actually in production. It's been around for a long time. This is kind of the Papa Bear grandfather of time series. So it's old, but it's still pretty darn reliable with some caveats there. You can keep this data forever. It's always stored at its original timestamp and precision, so you don't lose the data. We store integers. We store floating point values. We can also store strings. I don't think I put it up here. But it actually does a lot of good stuff, and it's all written on top of HBase, or now, thanks to the folks at Pythian and Google, you can use BigTable for it. So real quick, what are HBase and BigTable? They're just open source in the case of HBase, or hosted in case of BigTable. They're LSM-backed hash tables, essentially, sorted, and they're distributed. So they're key value row-based columnar stores. Sorry, I can't pronounce that at all. And it's always sorted, so it is, again, a giant hash table. The hash is split up amongst regions or tablets across multiple servers. It's atomic, so it aims for consistency and partition tolerance, but doesn't guarantee high availability. The reason for that is that if you split or you drop a server, you don't want to lose any writes, and they didn't want to go with the Cassandra model of eventual consistency, so you can't write or read from a specific region until it's brought up on another host. In HBase, and probably Google's case, it's really super fast when you're running in productions, within a couple seconds maybe. The benefits of HBase is that it allows you to scan across that hash table. You can walk it and iterate it. You can apply filters to pick out specific rows or specific columns. And again, it's all atomic too. So both HBase and Cassandra came out around the same time. There were different takes on Google's BigTable paper. And Cassandra went a slightly different way than HBase. But under the hood, Cassandra started off similarly, which is why OpenTSDB can kind of work with old versions of Cassandra. I'll talk about that in a bit. Anyways, the OpenTSDB schema is pretty simple. What we do, starting with 2.2, is that we add a salt at the start of a row key. Then we convert all of these metrics into unique identifiers, and we maintain a map of these strings to UIDs in a separate table in HBase or BigTable. And then we concatenate all of this information in the order of the salt, the metric, then a base timestamp, which is Unix epoch, and that's the top of the hour for raw data, or in 2.3 or 2.4, which is coming up, we've exported our rollup code, which allows you to store more data at a lower fidelity in these rows. Then it's followed by all of the tags that your identity includes. They're in a sorted order. So what this allows us to do is create a filter in HBase that says, okay, if I want 24 hours of data, I know I want this metric. You always have to specify metric. And then I may or may not want these tag combinations. And then you set up that filter and you just iterate over the rows, and HBase is going to pick out that data and send it back to the TSD, the process running. So all the data points for a specific time interval are stored within one row. They can either be individual columns, or they can be appended to a single column for more data compaction. We encode all of these with not any kind of super specific compression, but just VLE encoding for integers up to 64 bits. So we'll go from 1 byte to 8 bytes, or we'll do double or single precision integers, floating point values. We also store strings, and then with 2.4 we're able to store raw histograms also. And then 3.0 we'll be able to store many more things too if we need to. So the benefit of this schema is that, again, you can create that filter and scan over data. The UIDs save you space. The drawback to the schema, though, is that you do have to make those mappings between UIDs and schemas, which means you either have to hit the other table all the time to perform your lookups, or you have to cache that information. So that can be a pain. And also, depending, it's not as compressed in this format as it could be. If you look at Facebook's Gorilla, which we're going to be integrating with TSDB later on, they have a neat encoding scheme where they'll take a diff of diffs of the values beforehand, which is great in the in-memory store that they have, but in HBase or a disk-backed store, if you haven't written, if you don't have that last value in memory, and you want to compute your diff, you're going to have to go hit disk, load it into memory and page cache, perform that diff, write it back, and then hopefully it's flushed out. So we can't immediately implement that strategy in HBase. It's not very easy unless we do some funky coprocessor stuff, which we haven't gotten to. But instead, we rely on HBase's native compression or pluggable compression. And at Yahoo, we've been using gzip, and we get about 80% compression on our data. And I'll get to that slide in a second. But we get really good storage throughput with that. So this is another way to look at the column or the layout of TSDB data. You have your row keys. I didn't put salt in here. It's no biggie for this case. But you have metric, your times, and then you have all of your columns here. In each column, you have a qualifier, which is kind of the header of the cell. And you have encoded in that an offset from the base time in TSDB, and then you have a value. And this offset also includes the length, the VLE encoding, or the type of value stored in there. And then you have a bunch of different columns in there. So when you issue a TSDB query, you might say, I want to start at time 1, end at time 2, and I want metric M1, and then I want anything that contains this tag 1, tag value 1, and then I do want only time series with that tag. That's a new explicit tags feature in 2.2, I think. And when you scan over the table, it's going to say, okay, this row matches, so give me all those columns. Not a match, not a match, another match, give me those columns, and then bam, I'm done. So that's kind of how HBase works on there. So as I said, TSDB has been around for a long time. It's been used at a lot of big internet companies. One of them, Salesforce, it's the basis of their monitoring system. They're pushing about 2 million data points per second right now into their HBase cluster, and it's the basis of Salesforce's Argus, which is a neat open source monitoring tool you can take a look at. It'll do all of your storage, alerting. I think it has dashboarding capabilities, all that fun stuff. So if you've got HBase running, you can run this. I don't think it could integrate with BigTable also if you want to run hosted. And then at Yahoo, it's the backbone of our monitoring infrastructure as well. So we do have streaming in front that takes and computes a lot of values and does the alerting, and then we store all of that data into HBase, and we have dashboards on top of that. So we're averaging at steady state about 10 million writes per second. This is individual values coming into our system, and then at peak we hit about 18 million per second. And then we have about 3 petabytes uncompressed in storage, and it compresses down to about 500 terabytes in our clusters there. And we have over 1 billion continually active time series, and then we have a lot more junk time series that we've had because the system's been up for a couple of years now. And we're also the leading kind of committer and promoter of OpenTSDB in the community. There are a whole bunch of other companies using it, of course, and hopefully they're still using it. Some people may have moved off, looking at the flashiest new stuff that's out there. So what are some of the benefits of it? You can run it on HBase, HDFS yourself if you have that, if you have experts in-house. Because HBase is a beast, as the Python guys pointed out. You have to turn up, if you want replication and distribution, you have to turn up HDFS, name nodes, data nodes. Then you have to run HBase on top of it with HBase master, master slave. Then you have to have all the data nodes running. You have to tune it a lot to get it to really perform nicely. And then you have to run your TSDs on top of that. So as an alternative, you can now run it on BigTable. All you have to do is go talk to Google Cloud and say, hey, spin me up a BigTable instance, and give them your credit card or another form of payment, I assume, and then point your TSDs at it, and you're off and running. It also has support, again, for annotations, distributed histograms in 2.4, roll-up and pre-aggregate support, and built-in graphing. It has a marvelously beautiful interface. Just kidding. For graphing, it's ugly as hell. So most people go to Grafana. The interface in TSDB is kind of good for debugging. We're going to keep it that way, even in 3.0, just a debugging UI, and then other people can do the real good stuff with dashboarding and all that. Drawbacks, of course, complexity, UID resolution, all of that, HBase stability in some cases, also caching issues in TSDs itself, backlogging if HBase is splitting, all that fun stuff, and high cardinality is still an issue for HBase. If you have millions of unique tag combinations and you say, all right, show me a plot for each line for these million data points, TSDB and HBase won't do very well with that. Mostly in that case because of serialization. It's just going to blow up. So what's coming up in 3.0, we're starting a whole rewrite of TSDB 3 that's splitting it up into different libraries. One of the things that we'd like to accomplish with this is have kind of a generic time series library in Java that anybody can use to plug into or query different database systems, time series data and all of that, and perform the standard arithmetic operations on top of it, all that fun stuff. So we're adding distributed queries, multi-cluster queries. Some of this code has been running in prod at Yahoo, and I'm just bubbling it up now and cleaning and sanitizing it. We also have time-based caching, like I talked about with Gorilla. Facebook system, it has 26 hours of data in memory. And it has shard capabilities, so you can run a Gorilla cluster. And so the idea is that we'll be using that as a write-through cache. So that if you're only requesting 24 hours of data or an hour, you're going to hit the in-memory store really quickly, pull it back, and be able to do your graphing. Or if you want a wider time range, you can look at that and then also look at HBase or other stores for more historical data. This is kind of the model that a lot of groups have been adopting. It's kind of Splunkish, if you're familiar with Splunk. You've got in-memory data and then cold storage and all that. We're finally getting the pluggable storage engines that we've been talking about for ages, but we finally got the interface for it. Right now we have support for HBase, Cassandra, and BigTable, but then we'll be able to implement different schemas on top of HBase or query something like Druid or Influx or things like that. And we've also been working on anomaly detection right now using the Yahoo eGADS library. Which is a pretty nice little time series library, but it doesn't have a lot of the integrations that we need. So I can't just talk about TSDB because there's been an explosion of time series databases in the past couple of years here. One of the earlier ones is a project called Druid that's more of an analytics columnar store. That's actually very big at Yahoo also. I know we hired some of the architects there and we've got a team. And it's been used a lot for analytics storage. So your website click-throughs, advertising, traffic analysis and all of that. It has a slightly different take than HBase and other stores in that it takes and breaks up everything by time chunks and what they call segments. And then they store all of the indices and everything in that segment uniquely to that segment. And they have a bitmapped index mapping strings to the actual values and data, so it's fairly compacted. And if you ever need to delete or get rid of data, you just delete the segment, and that's all of the data stored in that segment is gone. It also has tiered storage, so it can maintain some of that information in memory. It can contain it excuse me, I think even locally on the client a little bit, and then it can also go to backed other data stores like S3 or HDFS. So the great thing about this is that it's very scalable. You can do a lot of cool OLAP slicing on it, all of that information. It also supports timed rollups and aggregations. The drawback is that it has a very complex infrastructure. It's similar to HBase in that you have Zookeeper for coordination, you have MySQL for metadata lookup, you have various historical nodes, query nodes, in-memory nodes that you have to spin up. And it's proved that at Yahoo it's very expensive to run to get high performance from it, but that expense is worth it for like cost or revenue generating units, but for something like monitoring where you may not need instantaneous query results, TSDB is a lot more cost performant. You can still store a lot more data in there. Another one that everybody's been talking about lately, kind of the replacement for Graphite nowadays, is InfluxDB. And it's got some really cool tech. It's all written from the ground up in the Go language, another Google offshoot. And they use pretty much just standard LSM, and then they follow in a similar format, Druid, that they slice up the LSM chunks by time now. So almost all of the time series data engines are going log structured merge because you can achieve super high write throughput. You can make it pretty consistent and not worry about losing data too much. But the drawback is that queries are going to be a little slower in general, and it won't support a huge query load. And for most instrumentation, that's perfectly okay, because a lot of times you're going to be ingesting tons and tons of data, but then you'll have a few dashboards on it, or you'll have a few queries on top of the data that's in there. If you want to do any real heavy processing with time series data, a lot of times you're going to want to turn to streaming systems like Storm, Spark, Flink, etc. So Influx is really nice. It has a SQL-ish query language. It supports time series rollups too. It supports nanosecond time precision, which is, I think, one of the only databases right now that does that for customers who need to timestamp stuff that specifically. Some of the drawbacks are that it doesn't have very good clustering support right now. I was talking with the guys, and they're trying to get up to about 1 million data points per second clustered, but haven't gotten to that yet. But also the clustering is going to be paid because they have a company around Influx now. It's also going to have the same cardinality issues as other data stores. And then, of course, there are many more data stores you can take a look at. There's Dalmatiner DB. Somebody wrote based on React, and I think Erlang. Timely, I've looked at a little bit. Or I haven't actually looked at yet. Prometheus, not specifically a time series store, as I mentioned in the keynote the other day. But there's this list down here. We'll be posting the slides later. This guy's been doing a good job of keeping track of all the new time series databases coming out there. And then, of course, you can go back to RDBMS. At Yahoo, the version of monitoring that we had just before OpenTSDB was still based on heavily sharded MySQL. We had a couple hundred machines around. We had different clusters dedicated to different groups within Yahoo. And we abstracted all of the metadata, those strings and stuff, into different tables that were shared. And we were able to get pretty good throughput on a single server. And share it across. Nowadays, there are new companies and open source projects like Timescale and Citus Data that are doing time series on SQL. So you can, if you're definitely stuck in a SQL world, you can give it a whirl, and you can deal with time series data that way. But if not, then you still may want to look at other solutions. So I wanted to thank the folks at Pythian and Google for their BigTable support. I wanted to thank the engineers on the monitoring group at Yahoo, and all the open source contributors who've been using OpenTSDB and patching it and trying to make us work better. You can contribute, check out the website, mailing list. We're on Google Groups and all that. And if you have any questions, now's the time. Anything? Sure.
I think you mentioned screen search per second in Yahoo.
So our HBase cluster consists of about 200 machines, and we're getting that 18 million write throughput at peak load. Per second. So I was talking with the Facebook, pardon? 200 machines, yeah. And I was talking with the Facebook engineers. They were playing with open source HBase 2 for a similar use case, and they were able to push HBase to about 40 million writes. But I think they didn't have any queries running at that point. So you can definitely dump a lot of data in there pretty quickly, and it works well. But if you want to read it out, you need to balance it. So we run our HBase nodes at about an average of 50% CPU. When we're writing at that rate. So that leaves enough room for about 100 queries per second against the data store there. And that query rate is low, again, because we do all of our time series processing in Storm for alerting and analytics. No, because if you're going to have that many tags, in general, it's going to be super sparse data, and you'll want to look at something more along the lines of, I think, ClickHouse or Druid for doing analyses, because then if you're going to be slicing along those columns, you're going to want all of that data arranged by column and duplicated in that case. So generally, for these time series, we recommend keep it down to, a few dozen tags, and I think our limit at Yahoo is 32 tags right now. It's configurable. As of 2.2, yeah, there's a config. It used to be hard-coded, but now you can add more. And yeah, we've been running okay, and we also do another drawback with UIDs and TSDB, of course, is that when you spin up a TSD, you're going to have your UIDs on a specific number of bytes. So by default, it's 3 bytes. Nowadays, I'm recommending everybody bump at least the tag values byte up to 4 or 5. And then at Yahoo, we're also facing a problem that we bumped up our bytes to 4 bytes. So we're feeling the pressure now of that 4 billion unique values limit for tag values. So 3.0, part of the impetus for the rewrite is so that we can split the data into other tables with bigger UID spaces and be able to query across both of them. So we know that's a problem a lot of users are facing who have been running TSDB for a long time.
You mentioned, like, in 3.0, there will be like anomaly detection algorithms. Since like OpenTSDB is mainly like you said, the backend, the storage backend, it's not like a dashboard or even like an alerting system. How do you see that working?
So the way we have it running right now in production at Yahoo is that we have the EGAD system as part of the query layer, and when you issue a query, you say, okay, I want the results pulled through these models, and you configure the different models. We haven't gotten to the machine learning bit yet where we do the matching and rejiggering of the values or the tuning yet. But we read that data, and that's our only query time-based alerting system right now. So we generate the models, and in general, we'll do period over period, say, trending analysis, and we'll fetch a day's worth of data for that. We'll build the model and what the values are expected to be for the forecast, store that forecast in a cache. Right now, the implementation that we're going to upstream is a Redis cluster-based cache. And then the next time a query comes through for a specific time point, we'll pull the value from TSDB and then evaluate against that forecasting, and then Storm sends an alert to somebody. In the future, we'll have Storm taking and evaluating directly against that model that we built from the TSDB data. And then it's also tied into the query layer so that users can request a query and graph the various models against each other in real time. The model generation has been super quick for us. Most of the problems are around tuning the queries so that somebody doesn't say, okay, I want all 200,000 hosts in the mail system, which would just blow up all of the systems, query systems. Yeah. Cool. Yep.
Any plan to implement any record reader or something like that so that you can access the value like from the specific format through MapReduce or Spark?
Yeah.
There have been cases that you want to load all time series points somewhere and then do some funky stuff that you can't do right now. So, is that not that?
Yeah, that's kind of the plan that I have for the 3.0 query layer, is so that you can do a more, do you kind of mean like a more chunked loading and processing, like a MapReduce? Because, yeah, right now one of the drawbacks of TSDB is that it all has to load all of that data in memory, then process it. The new layer lets you query very broadly and do some aggregation down lower at the various nodes, and then kind of MapReduce it back up. And then it also supports chunking too, kind of like a pig or something like that, where you can say, all right, I do want a year of data. I know that's not going to fit in memory. I'm going to start with maybe daily chunks and then work and wrap all that back up. So I could definitely use help on the new API. It's already going up in the 3.0 branch. Some of the code's super ugly, and I'm reworking it. But if anybody has feedback for me, constructive feedback, don't just look at it and say, you suck, we're going to build a new database. That's not cool, you know? Just come and say, hey, you could probably do this better, and then, yeah, I'm always, always appreciative of that kind of help. Sure. So our pipeline at Yahoo, what we have, the whole monitoring pipeline is that we have collectors in all of our data centers that get the data pushed to us from the host. Those collectors then are pushing data into a proprietary Yahoo messaging queue system, and that's all brought into 2 different data centers and loaded into Kafka, where we queue it. From Kafka, then, we have storm topologies that users will write rules in Git and commit this DSL to a Git repo. And then our topologies look at those configs, restart whenever they need to. And as data is flowing through, depending on the windowing and the configs and all of that, we'll process it based on the thresholds the users have and then send those alerts, if they're triggered, off to another Kafka queue from which consumers then read the alerts and then do the lookup on the rules to say, oh, this has to go to Ops Genie, this has to go to somebody's email, this has to trigger automation, that kind of stuff. That library, the Yahoo Storm Code library, is something that we're in the process of cleaning up and open sourcing so that other companies can use it. If you're looking for a quicker alternative, I think Symantec, the antivirus and everything company, has a similar storm infrastructure that they've already open sourced, so you can play with that. Also, ArgusDB doesn't do streaming processing, but it does do batch alerting. And all those tools will integrate with TSB, I believe. And there's also a project from a Stack Exchange called Bosun that's a monitoring system based on TSB. So that's something to look at, too. Cool. Any other questions? So, yeah, take a look at OpenTSDB and also take a look at all the other great time series data stores that are out there. Like I said, I'm not trying to make money off TSDB or anything, and if there's something better out there, use it. If you find it's better than TSDB, let us know why. That'll help us make TSDB better in the future, and that'd be great.
You said 200 servers for 1 million events. Are those TSB servers, or that includes your HBase?
Those are HBase servers. Actual TSD servers, we only have maybe, I think we have 17 query servers in each colo. And then we have about 100 little VMs that the TSDs run on that consume off of the Kafka queue. And each little VM can do about up to 300,000 writes per second if we need it to. We run it a lot cooler because, and one of the benefits of Kafka too is that we partition everything and hash all of our metrics so that they're split amongst, I think, 200 or so partitions. So each TSD is only consuming a partition or 2. And most of that is partly due to steal time, which if you're running a VM and you don't know what steal time is, or if you're using a hosted service, be it AWS, Google, or anything, go out and look up steal time now because it's going to kick your ass someday and you won't know why. How many people know about steal time, actually? Okay, so some of you do. If you don't, that's my public service announcement. Forget TSB, forget time series right now. Go look at steal time. And then after that, it's Kafka performance that we do that sharding for, the partition. But any kind of time series system that you have, any database, it does definitely help to have a queuing system in front of it to absorb downtime. And we found that Kafka's been pretty reliable and fault tolerant. Cool. All right. Well, thanks everybody for coming. And